Picture a void, not darkness. Darkness implies the absence of something. This is older than darkness. This is the universe at 280 million years of age, a cosmos so raw, so primordial, so thick with the residue of its own violent birth, that the very concept of a galaxy, a structured, organized, chemically mature collection of hundreds of millions of stars, should be impossible. The universe has not had time to build one, not here, not yet. The hydrogen fog that blankets everything is barely beginning to thin. The first stars, enormous and furious and brief, are only just igniting and dying and seeding their ash into the surrounding void. The cosmos is an infant, a newborn almost and yet, hanging in a patch of sky so unremarkable that it lies in the constellation Sextans. There is something, a faint smear of infrared light, a signal so ancient that the photons carrying it have been stretched by the expansion of space itself until they arrive at our detectors not as the ultraviolet blaze they were born as, but as the deep red whisper of the infrared, light so old it has forgotten its own colour. The James Webb Space Telescope catches it, measures it, analyses it, and the answer it returns is so extraordinary, so thoroughly in violation of what we believed we understood about the early universe, that the scientists who first processed the data called it, with complete scientific seriousness, a miracle. Its name is MOM-Z14. It is the most distant galaxy humanity has ever confirmed, and it should not exist. How did a galaxy this mature, this luminous, burning at 100 times the brightness our best models predicted anything could achieve at that epoch, come to be so early? Why does it contain heavy elements that require multiple stellar generations to forge, and yet those generations could not possibly have had time to live and die? And what does it mean for everything we thought we knew about how the universe grows up? We are about to find out, and I promise you, the answer is stranger than the question. There is a particular kind of patience required to pursue the beginning of everything. It is not the patience of a person who waits for a bus, or a scientist who waits for a result. It is the patience of a civilization, one that must first agree that the question is worth asking, then fund the asking of it across multiple decades, then build the instrument capable of detecting an answer, and then wait for that instrument to unfold itself in the frozen silence of space, at a distance of 1.5 million kilometers from everything it was ever meant to protect. The James Webb Space Telescope is that instrument, and its story, before a single photon of ancient light ever passed through its golden mirrors, is already one of the most remarkable engineering narratives in the history of our species. To understand why JWST represents such a radical departure from everything that came before it, you need to understand what the universe's earliest structures look like from our vantage point on Earth, or just above it. The universe has been expanding since the Big Bang, now estimated to have occurred approximately 13.8 billion years ago. That expansion does not merely move galaxies apart from one another, it stretches the very fabric of space itself, and in stretching space it stretches the light travelling through that space. A photon emitted by an early galaxy as ultraviolet radiation, high energy, short wavelength light, begins its journey across the universe with a wavelength of perhaps 100 to 200 nanometers. But as it travels through 13.5 billion years of expanding space, that wavelength gets pulled, elongated, redshifted. By the time it reaches us, that same photon has a wavelength not of 150 nanometers, but of 2000 nanometers or more, deep in the near-infrared, far beyond what the human eye can perceive, and beyond the sensitive range of most conventional astronomical instruments. This is why the Hubble Space Telescope, for all its extraordinary achievements, and those achievements are genuine and numerous and world-transforming, could only peer so far back in time. Hubble was designed primarily as an optical and ultraviolet telescope. It could stretch into the near-infrared at its limits, but those limits were hard. The galaxies of the earliest universe, the ones formed within the first 300 to 500 million years of cosmic history, were functionally invisible to Hubble's primary instruments. They existed in a spectral range Hubble was never built to penetrate deeply. JWST was built precisely for that range. Its primary mirror, 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments, is not merely larger than Hubble's 2.4-meter mirror. It is designed to gather light at wavelengths between 0.6 and 28 micrometers, covering the full near and mid-infrared spectrum where the universe's earliest light now lives. The choice to coat those mirrors in gold is not decorative. Gold reflects infrared light with an efficiency that aluminium or silver cannot match, and in the detection of the faintest signals from the most distant objects in the known universe, every fraction of a percentage point of reflective efficiency is the difference between seeing and not seeing. But there was a profound engineering problem embedded in this plan, and it is one that very nearly made the entire mission impossible to execute. Infrared astronomy, detecting heat radiation from objects at cosmic distances, requires the detecting instrument itself to be cold, extraordinarily cold. If the telescope and its cameras operate at room temperature, or even at the temperature of low Earth orbit, the infrared heat they emit from their own structure overwhelms the faint signals from distant galaxies. The telescope would essentially be blinded by its own warmth. To detect infrared light from objects formed 280 million years after the Big Bang, JWST's instruments need to operate at temperatures close to minus 233 degrees Celsius, approximately 40 degrees above absolute zero. Achieving this in space requires one of the most audacious pieces of engineering ever constructed and successfully deployed by human hands: the sunshield. JWST's sunshield is a 5-layer structure of a material called Captain, coated in aluminium and silicon, spread across an area roughly the size of a tennis court, 21 by 14 meters when fully deployed. Each layer of the sunshield is thinner than a human hair. Together, they reduce the heat reaching the telescope from the combined radiation of the Sun, the Earth, and the Moon by a factor of approximately 1 million. On the sun-facing side of the sunshield, temperatures reach 110 degrees Celsius. On the telescope side, directly behind the shield, the temperature drops to minus 233 degrees. 5 layers of material thinner than a human hair maintain a temperature differential of 343 degrees Celsius continuously in the vacuum of space at 1.5 million kilometers from Earth. The deployment of that sunshield was, to my mind, one of the most terrifying and triumphant moments in the history of robotic engineering. JWST launched on Christmas Day 2021 aboard an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana, a launch that had been delayed from its original target of 2007 repeatedly and expensively across 14 additional years of development, testing, redesign, and financial escalation from an initial projected cost of roughly $1 billion to a final mission price tag of $10 billion. The sunshield alone required 139 of JWST's 178 single-point failure release mechanisms to fire successfully. In sequence, without a single failure, there were 70 hinge assemblies, 8 deployment motors, and roughly 400 pulleys involved in its unfolding. Any one of those mechanisms failing meant the mission, the entire $10 billion mission, would fail with it. There was no repair option, no servicing mission, no second chance. They all worked. Over the course of approximately 2 weeks following launch, the telescope unfolded itself in a sequence that engineers had rehearsed thousands of times on the ground, but had never fully simulated in the actual vacuum and cold of space. The sunshield unfurled, and tension, the secondary mirror deployed on its tripod. The 18 primary mirror segments moved into alignment with a precision measured in nanometers. And on July 12, 2022, the first full-colour science images from JWST were released to the world. A deep-field image of galaxy cluster SMACS 0723 that showed structures billions of light-years away with a clarity and depth that left astronomers, including those who had spent their entire careers building the instrument, visibly shaken. There is a famous moment from that day. NASA Administrator Bill Nelson, presenting the first image at a press conference at the White House, began by saying that what we were looking at represented light from 13 billion years ago. And then he paused, not for dramatic effect, as far as I can tell, but because the number seemed to need a moment to land for him, as much as for anyone in the room. 13 billion years. In a single image, assembled from the light gathered by a golden mirror in less than 5 hours of total observation time, we were looking at galaxies that had begun their lives when the universe was less than 1 billion years old. That was the opening act. What came next was something nobody had quite predicted. Within the first few months of JWST's science operations, something strange began emerging from the data. Astronomers studying the very early universe, not the billion-year-old structures visible in that first dramatic image, but the much older, more distant, more primordial ones, began finding galaxies. Not just a few, not the trickle that theory predicted. They were finding them in numbers and at brightnesses that the models said should not be there. The theoretical framework that describes how the universe assembles itself, how gas clouds collapse under gravity, how stars ignite within them, how those stars gradually organize into galaxies. That framework had precise predictions about how bright and how numerous early galaxies should be. JWST was finding roughly 100 times as many as it should have. The murmur through the astronomical community in late 2022 and early 2023 was unlike anything in recent memory. Papers appeared on the preprint server Axiv in rapid succession, each one pointing to the same uncomfortable conclusion. Either the observations were wrong, or the models were wrong, or both. Some researchers, cautiously, but audibly, began using a phrase that in science carries the weight of a verdict. The standard model might be in trouble, but there was a problem with that verdict, and understanding the problem is essential to understanding why the universe JWST is revealing to us is simultaneously more comprehensible and more strange than it first appeared. The models were not simply wrong, they were incomplete, and the difference between a wrong model and an incomplete one is, in science, the difference between a crisis and a discovery. What JWST had found in those first overwhelming months of data was not the death of the lambda CDM cosmological model, the standard model of cosmology describing a universe of cold, dark matter, ordinary matter, and a cosmological constant driving accelerating expansion. What it had found was the outer edge of that model's predictive range. The regime in which the details of how individual galaxies form stars, how black holes at their centers behave, and how those processes interact with the surrounding gas all become critical, and all had been imperfectly captured by prior simulations. The truly extraordinary discoveries were still coming, and the most extraordinary of all, confirmed on May 16, 2025, at a redshift of z equals 1444, would force us to ask questions that none of those careful incremental recalibrations could fully answer. The questions MOMZ14 raises are not questions about parameter adjustments in galaxy formation models. They are questions about when, exactly, the universe learned to make the things it makes, and whether the timeline we have drawn is even close to correct. Before we can confront those questions, we need to understand the terrain. We need to understand what a redshift of 14.44 actually means. We need to understand what we should find at 280 million years after the Big Bang if our models are right. And we need to understand why, when JWST turned its golden eye toward that epoch of cosmic history, it found something that one of the team's own senior researchers, Dr. Rohan Naidu of MIT's Kavli Institute for Astrophysics and Space Research, described in the official publication, not with the measured vocabulary of a scientific paper, but with 3 plain words that the astronomy community has not stopped discussing since: a cosmic miracle. To appreciate why MOMZ14 is so deeply, structurally wrong by the standards of everything we thought we understood, you need to walk through the universe at the age it was when this galaxy already existed. Not the old, vast, galaxy-filled universe we inhabit today, with its hundreds of billions of galaxies arranged in filaments and voids and clusters, a cosmic web spun across 93 billion light-years of observable space. The universe of 280 million years after the Big Bang is a fundamentally different place. It has a different texture, a different chemistry, and a different relationship between matter and light than anything that exists today. And the key to understanding why MOMSI-14 is so disturbing is understanding how little time there had been for anything complex to build itself. The story begins, as cosmologists always insist it must, at the very beginning. In the first instance after the Big Bang, the first fractions of a second, the universe was an undifferentiated plasma of quarks, leptons, photons, and the other fundamental particles, all compressed to temperatures and densities so extreme that the very concept of matter as we understand it did not yet exist. Within the first 3 minutes, as the universe expanded and cooled below roughly 1 billion degrees Celsius, protons and neutrons bound together into the first atomic nuclei, hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, produced a universe that was approximately 75% hydrogen by mass and 25% helium, with essentially no heavier elements whatsoever. No carbon, no oxygen, no nitrogen, no iron, no silicon. None of the elements that eventually make planets, and biology, and the breathable air in the room where you are listening to this. At the moment of its birth, the universe contained nothing heavier than lithium, and even that was present in only the tiniest quantities. The universe remained a hot, dense plasma for approximately the next 380,000 years. During this entire period, the universe was opaque. Light could not travel through it, because photons were constantly scattering off the free electrons in the plasma. Then, at around 380,000 years after the Big Bang, the universe cooled to a temperature of approximately 3,000 degrees Celsius. At that temperature, a threshold the universe crossed at a moment cosmologists call recombination. Protons and electrons were finally able to combine into neutral hydrogen atoms without immediately being torn apart again by the surrounding heat. When the electrons locked themselves into atoms, the photons they had been scattering off were suddenly free to travel. The universe became transparent to light for the first time. That moment of first transparency is encoded in the universe we see today as the cosmic microwave background radiation, the faint afterglow of that first light, now redshifted all the way from visible to microwave frequencies by 13.4 billion years of cosmic expansion, still detectable in every direction of the sky. The CMB is the universe's baby photo, a snapshot of its face at 380, no 0 years old, and what it shows us is a universe that was at that moment remarkably smooth. The temperature variations across the CMB, the slight fluctuations that represent the seeds of all future cosmic structure, amount to no more than 1 part in 100,000, 100,000th of a degree Celsius of variation across the entire observable sky. The early universe was, by any reasonable measure, almost perfectly uniform, almost. That tiny 100,000th of a degree variation was enough. Those slight overdensities, regions where matter was fractionally more concentrated than average, were the seeds from which gravity would slowly, patiently, painstakingly assemble the first structures, and in the 280 million years between recombination and the epoch from which MOMSI-14's light now reaches us, gravity had been working. But working is perhaps too casual a word for what gravity faces in this environment. In the period immediately following recombination, a phase cosmologists call the cosmic dark ages, there was no light in the universe. None. The CMB photons had decoupled and were flying outward in every direction, leaving behind a universe of neutral hydrogen and helium gas, slowly being pulled into clumps by the gravitational influence of dark matter, the mysterious, invisible form of matter that does not emit or absorb light, but constitutes approximately 27% of the universe's total energy content. Dark matter had begun clumping even earlier than the visible gas, forming the gravitational scaffolding into which ordinary matter would eventually fall. These dark matter concentrations are called halos, and they are the invisible cradles in which every galaxy in the universe is born. The first dark matter halos massive enough to retain their gas, to not have the gas blown outward by the heat of the surrounding intergalactic medium, are estimated to have begun forming somewhere between 100 and 200 million years after the Big Bang. This is already an extraordinarily tight timeline. In the first 100 million years of cosmic history, the universe had to cool from billions of degrees to a few hundred degrees. Dark matter had to begin concentrating into halos massive enough to hold gas, and that gas had to fall into those halos and begin compressing toward the temperatures and densities required to ignite nuclear fusion. The result was the first stars, designated population 3 stars in the astronomical naming convention, where population I refers to stars like our Sun that formed recently from gas already enriched with heavy elements, and population 2 refers to older stars formed from gas containing smaller but non-trivial amounts of those elements. Population 3 stars formed from gas that was pure primordial hydrogen and helium, essentially untouched since Big Bang nucleosynthesis. They were, by all theoretical accounts, extraordinary objects, because the cooling mechanisms available to gas clouds depend in part on the presence of metals, the astronomers' term for any element heavier than helium, and because pure hydrogen-helium gas cools less efficiently, population 3 stars are thought to have formed from gas clouds of much greater mass than stars formed today. The estimates for typical population 3 star masses range from roughly 100 to over 1.00 times the mass of our own Sun. Some theoretical models suggest the most extreme examples may have been tens of thousands of solar masses, objects so massive and so hot that they burned through their hydrogen fuel in perhaps a few million years before dying in catastrophic supernovae or collapsing directly into black holes. Here is the crucial point, and it is the point from which the MOMZ14 problem unfolds with its full disorienting force. When a massive star dies, whether in a supernova explosion or through other processes, it disperses the elements it has synthesized in its nuclear furnace into the surrounding gas. A star born of pure hydrogen and helium, and massive enough to fuse hydrogen all the way through to oxygen, neon, silicon and iron, will die and leave behind an expanding shell of heavy elements, oxygen, carbon, nitrogen, the building blocks of chemistry as we know it. Those heavy elements mix into the surrounding gas cloud, and when that enriched gas subsequently collapses into a new generation of stars, those new stars burn differently, live differently, and when they die, they enrich the gas further. This process, stellar nucleosynthesis, the manufacture of heavy elements inside stars and their dispersal into the interstellar medium, requires time. Multiple cycles of star birth, stellar evolution, and stellar death must occur before a galaxy's gas becomes meaningfully enriched with elements heavier than helium. The first generation of stars must form, live their brief but luminous lives, and die. Their enriched debris must disperse and cool and recollect. A second generation must form from that enriched material. And so on, at 280 million years after the Big Bang, we are, according to every standard model of galaxy formation, looking at a universe that has had time, at most, for perhaps 1 or 2 of those cycles. We are looking at a universe in which true chemical enrichment, the kind that produces detectable abundances of oxygen, nitrogen and carbon in a galaxy's interstellar medium, should be a rare and precious thing, present in only trace quantities in the most fortunate and most efficiently forming corners of the cosmos. The standard lambda CDM model, combined with our best models of star formation and galaxy evolution, makes a prediction about what we should see at this epoch. It predicts that galaxies at redshifts above approximately 10, corresponding to ages of the universe below roughly 480 million years, should be small, dim, chemically primitive, and relatively few in number. They should be the universe's first rough drafts, clumpy, irregular concentrations of young stars, burning through pristine hydrogen and helium gas, with little to show for their brief existence beyond the raw ultraviolet output of their massive first-generation stellar populations. What JWST found, beginning in 2022 and continuing with relentless, almost taunting regularity through 2023, 2024, and into 2025, was something different in almost every measurable dimension. Galaxies at redshifts of 10, 11, 12, 13, and eventually 14 were not rare. They appeared in survey after survey, in numbers roughly 100 times greater than the models predicted. They were not dim. Many of them blazed with luminosities that implied stellar masses, the total amount of matter locked up in stars, far greater than anything the models said should exist at those early times. They were not chemically primitive. Some of them showed clear spectroscopic signatures of nitrogen and oxygen, elements that require multiple stellar generations to produce in significant quantities. And then came JWST 14-0. In January 2024, the NIRSpec instrument aboard JWST stared at a single patch of sky in the Fornax constellation for nearly 10 hours. The target was a faint candidate galaxy, one of many flagged by earlier imaging surveys as a potential extremely high redshift object, based on the distinctive way its light suddenly cut off at wavelengths shorter than the Lyman break. The spectral feature caused by neutral hydrogen absorbing the highest energy photons. When the spectrum came back from JWST 14-0, the redshift measured was 1432. The light now reaching JWST had been emitted when the universe was approximately 290 million years old. Stefano Carniani, of the Scuola Normale Superiore of Pisa, one of the lead researchers on the paper, would later describe his reaction with the kind of understated precision that scientists use when words are genuinely inadequate to the feeling. He said he was astonished. He said it opened a new view on the first phases of galaxy evolution. He said the evidence that a galaxy was already mature in the infant universe raised questions about when and how galaxies formed. That word, mature, is the key that opens the entire problem. JWST 14-0 was not a faint, dim, primitive smear of light. It was spatially resolved, meaning its light extended across a physical region of approximately 600 light-years in diameter, far larger than anything that should have had time to organise itself at this epoch. Its luminosity implied a stellar mass, the total mass of stars it had already assembled, of somewhere between 400 million and 600 million times the mass of our own Sun. And then, in March 2025, ALMA, the Atacama Large Millimeter Submillimeter Array, an extraordinary radio telescope system in the Chilean Atacama Desert, confirmed something even more startling. JWST 14-0 contained oxygen, not trace oxygen, not a marginal detection at the edge of statistical significance. Clear, unmistakable oxygen emission, at a level 10 times greater than the most optimistic theoretical models predicted for a galaxy of its age. Sander Schaus, a PhD candidate at Leiden Observatory and the first author of one of the two independent ALMA papers, put the situation into plain English. It is like finding an adolescent where you would only expect babies, 10 times more heavy elements than expected, more than 400 million solar masses of stars, a diameter of 1600 light-years. All of this in a galaxy formed no later than 290 million years after the Big Bang, in a universe that should have been biologically, chemically, and structurally incapable of producing any of it. Now, hold that picture in your mind, because something even more extreme was coming. On May 16, 2025, the MOM survey, the Mirage or Miracle survey, designed specifically to spectroscopically test whether these bright, anomalously luminous early galaxy candidates were real or artifacts of some photometric error, confirmed a new record. The team, led by Rohan Naidu of MIT's Kavli Institute, announced the spectroscopic confirmation of MOM Z14 at a redshift of Z equals 14.44, not 290 million years after the Big Bang, 280 million years, 10 million years earlier, and this galaxy was not just older, and therefore potentially explainable by fine-tuning the models at the margins. It was, in the team's own published assessment, 100 times brighter than theoretical studies had predicted anything at that distance, and epoch should be. The name MOM Z14 encodes both the survey and the galaxy's redshift. The survey is called Mirage or Miracle because its fundamental purpose was to determine whether these anomalously bright high redshift objects were real or mirages, artifacts of photometric contamination, lensing, or instrumental effects. The implication of that survey name was not rhetorical. It was a genuine scientific question. Were these things real, MOM-Z14's spectroscopic conformation answered that question with crystalline precision. The galaxy's redshift of 14.44 was confirmed not by a single spectral feature, but by multiple emission lines of nitrogen, carbon, helium, and oxygen in various ionization states, each one agreeing with the others to within the measurement uncertainties. This was not a mirage, it was, the team concluded, a miracle, or more precisely, it was something our best models of the early universe cannot account for. And three specific features of MOM-Z14, when examined together, constitute a challenge to standard cosmological models that is qualitatively different from, and considerably more severe than, the earlier JWST galaxy abundance problem. The first feature is its luminosity, 100 times brighter than any pre-JWST model predicted. Even accounting for the four factors that explain the broader overabundance of early JWST galaxies: optical overperformance of the telescope, improved simulations that include rare overdense regions, bursty star formation and AGN enhancement. MOM-Z14's brightness at this specific epoch pushes or exceeds the limits of all four explanations simultaneously. The second feature is its chemistry. Our MOM-Z14 shows clear nitrogen enrichment, elevated nitrogen levels that, just like the oxygen in JWST 14.0, require multiple stellar generations to produce. At 280 million years after the Big Bang, there is not a standard, consensus-accepted mechanism that produces those abundances within the available time. The third feature is perhaps the strangest. MOM-Z14 is showing signs of clearing the neutral hydrogen gas in the space around it, ionizing its immediate cosmic neighborhood, at a time when the universe as a whole should still be deeply enmeshed in what cosmologists call the epoch of reionization, a period that standard models place as ending somewhere between 550 million and 1 billion years after the Big Bang. How is a single galaxy at 280 million years old punching a hole through the hydrogen fog of the universe? How has it gathered enough ionizing photons, enough ultraviolet light, to clear the intergalactic medium around itself, hundreds of millions of years before the universe as a whole is supposed to have managed the same feat? These are not questions that resolve themselves with a minor adjustment to a star formation efficiency parameter. These are questions that, taken together, suggest we may be missing something fundamental about how the early universe worked. And the terrifying possibility, the one that every honest cosmologist I have read in the past 3 years will acknowledge, even if reluctantly, is that what we are missing may not be a detail, it may be a chapter. Let me introduce you to the central paradox, which I will call the adolescent universe problem, because it is exactly what Sander Schauss was pointing to when he said it was like finding an adolescent where you would only expect babies. The problem is not simply that JWST found something bright and far away. It has always been the case that the universe contains objects that lie at the extreme tail of the distribution, things that are exceptionally rare, exceptionally luminous, exceptionally massive. Statistical extremes are not, by themselves, evidence of new physics. The universe is large, and rare things happen simply because there are so many places for them to happen. The problem is that the mathematics of the adolescent universe problem cannot be resolved by invoking rarity. It cannot be resolved by saying these galaxies are unusually lucky or unusually positioned in a particularly overdense region of the primordial universe. The magnitude of the discrepancy between what the standard model predicts and what JWST observes at redshifts above 12, and especially above 14, is so extreme that it places these galaxies outside the boundaries of what the statistical tail of any sensible model can produce. Here is the physics of the problem, stated as precisely as I can manage without becoming a textbook. The formation of a galaxy requires several sequential processes, each constrained by physical timescales that cannot simply be accelerated by wishing for a better outcome. First, a dark matter halo must accumulate enough mass to gravitationally hold on to baryonic matter, the ordinary hydrogen and helium gas, against the heating effects of the cosmic ultraviolet background radiation and the internal energy of the gas itself. The minimum halo mass for this, called the Jeans mass or the filtering mass depending on the context, places a lower bound on how small a seed can trigger galaxy formation. This minimum mass takes time to accumulate. Second, once the gas falls into that dark matter halo, it must cool. Cooling is the process by which a gas cloud radiates away its thermal energy, allowing gravity to compress it further without the internal pressure of the gas resisting the compression. The cooling rate depends sensitively on the temperature and density of the gas, and on its chemical composition. Pure hydrogen-helium gas cools primarily through two mechanisms: collisional excitation of atomic energy levels and Compton scattering off the CMB photons. Both mechanisms work, but neither works quickly. The free fall time, the time it takes for a cold gas cloud to collapse under its own gravity, is inversely proportional to the square root of the density. At the densities typical of primordial gas clouds in the early universe, this free fall time is on the order of tens to hundreds of millions of years. Third, once star formation begins, the stars themselves provide a powerful form of feedback, energy injection into the surrounding gas, that can slow or even halt further star formation. Massive stars emit enormous fluxes of ultraviolet radiation that ionize the surrounding gas, heating it and raising its pressure. Supernova explosions expel gas from the galaxy at velocities that can exceed the galaxy's escape velocity, literally removing the fuel for future star formation. This feedback is not a minor correction factor. In many galaxy formation simulations, stellar feedback is the dominant mechanism regulating how rapidly stars can form, and it acts as a brake on the process throughout a galaxy's life. The question that MOMZ-14 poses is this: how do you build, in 280 million years, a galaxy with a stellar mass comparable to the Small Magellanic Cloud, approximately 100 million solar masses, displaying elevated abundances of multiple heavy elements, burning with luminosity 100 times greater than the models predict, and punching ionized bubbles through the surrounding intergalactic medium? The Small Magellanic Cloud comparison is instructive. The SMC is one of the Milky Way's satellite dwarf galaxies, located approximately 200,000 light-years from Earth. It contains roughly a few hundred million solar masses of stars, accumulated over the entire lifetime of the universe. 13.8 billion years of star formation enrichment, feedback and recycling. MOMZ-14 has assembled a comparable stellar mass in 280 million years. That is roughly 2% of the age of the universe. The SMC took the remaining 98% of cosmic history to get to where it is today. MOMZ-14 appears to have accomplished the same thing in the opening 200ths of the universe's life. Now, you might reasonably ask, could this simply be a matter of scale? Could MOMZ-14's dark matter halo have been exceptionally massive, sitting in an unusually dense region of the primordial universe, concentrating mass faster than average? Could the star formation efficiency, the fraction of available gas that actually converts into stars, have been unusually high? The answer to both questions is yes, in principle, but the devil is in the quantification. Star formation efficiency is a number between 0 and 1. It represents the fraction of a gas cloud's mass that successfully converts into stars before feedback from those new stars disrupts the remaining gas. In the local universe, the universe we can study in detail, with resolved observations of individual molecular clouds and star-forming regions, star formation efficiency is typically between 1% and 10%. High-efficiency events, like intense starbursts triggered by galaxy mergers, can push this to perhaps 30% or 40% locally. The theoretical upper limit, set by the competing effects of gravity and stellar feedback, is somewhere around 100%. All the gas converts to stars, but this is considered unphysical in practice, because the radiation pressure from the newly formed stars always disrupts the remaining gas to some degree before it can all collapse. Some of the brightest early JWST galaxies appear to require star formation efficiencies approaching or even exceeding these theoretical upper limits. The numbers don't work unless the feedback is dramatically suppressed, or the gas density is dramatically elevated compared to local analogues. And even then, Even granting every possible extreme value to every relevant parameter, the models struggle to produce an object as luminous as MOMZ14 at a redshift of 14.44. The bursty star formation hypothesis offers a partial escape hatch. The idea here is that galaxies in the early universe did not form stars at a steady, continuous rate, but rather in violent bursts, periods of extremely high star formation rate, interspersed with periods of suppression as feedback from the newly formed stars expelled gas from the galaxy. During a burst phase, a galaxy could temporarily appear far brighter than its average rate of star formation would suggest, because the massive short-lived stars formed in the burst are enormously more luminous per unit of stellar mass than the long-lived lower mass stars that survive between bursts. If we happen to observe a galaxy during its burst phase, we see a misleadingly high luminosity for its actual stellar mass. This is a genuine and physically well-motivated effect, and it explains, at least partially, why some of the early JWST galaxies appeared initially to violate mass limits, but later turned out to be less massive than they seemed when more detailed modelling was applied. Several galaxies that generated headlines in 2022 as potential cosmological crises were subsequently reanalyzed with better data and found to be consistent with standard models once the bursty star formation and AGN enhancement effects were properly accounted for. But MOMZ14 resists this explanation in a specific and revealing way. The spectroscopic analysis of MOMZ14's light shows an ultraviolet slope, the shape of the spectrum across the ultraviolet wavelength range, that is inconsistent with significant contributions from an active galactic nucleus. An AGN typically produces a flatter, redder ultraviolet slope and extends the galaxy's light across a larger apparent area on the sky. MOMZ14's ultraviolet slope is steep and blue, and its light is compact and concentrated, the profile you expect from a burst of star formation, not from a central accreting black hole. So the AGN explanation for its anomalous luminosity is essentially ruled out by the data itself. Similarly, the very features that confirm MOMZ14 is experiencing a current burst of star formation, its emission line equivalent widths, the high degree of ionization inferred from the presence of triply ionized nitrogen, its elevated gas density estimated at roughly 20 times higher than the gas density measured in JD's GSZ140, confirm that this galaxy has already accumulated the stellar mass implied by its luminosity. This is not a galaxy that merely appears massive because of a temporary AGN flare or an unusual stellar population dominated by short-lived giants. It is a galaxy that has been building stars long enough to have assembled 100 million solar masses of them, and is currently building more at a rate that has increased by a factor of 10 or more within the last 10 million years. There is one more layer of the problem that deserves careful attention, and it has to do not with the galaxy's stellar mass or luminosity, but with its chemical fingerprints. Both MOMZ14 and JAY's GSZ140 show elevated nitrogen abundances. Nitrogen enrichment is an element-specific story that connects these two galaxies to one of the most exotic and theoretically compelling proposals in stellar astrophysics. Nitrogen-14, the dominant isotope of nitrogen, is produced in the interiors of intermediate mass stars, stars between about 1 and 8 solar masses, through the CNO cycle. It is not in significant quantities produced by the most massive stars or by the simplest population 3 stellar models. The presence of elevated nitrogen in galaxies at redshifts above 14 is therefore deeply puzzling, because it implies that either the stellar populations of these galaxies include generations of intermediate mass stars that have had time to form, evolve and die, which, at 280 million years, seems barely possible, or that there is another nitrogen production mechanism at work, one not captured by our current stellar evolution models. One proposal, gaining traction in the astronomical community since JWST began reporting these nitrogen-enriched early galaxies, is that the very early universe hosted a population of truly extreme stellar objects, supermassive stars, potentially with masses between 1,000 and 100,000 solar masses. These hypothetical objects, theorized for decades but never directly observed, are predicted by certain models to produce anomalously large amounts of nitrogen and other elements through a combination of nuclear burning and convective mixing processes that differ fundamentally from those in stars of ordinary mass. If supermassive stars existed in the early universe, if the dense, turbulent conditions of those primordial gas clouds could produce stellar objects far beyond the mass range of anything we have ever directly studied, then many of the chemical anomalies JWST is detecting might be explained. In January 2025, a team using JWST published what they described as the first compelling evidence for the existence of such supermassive stars, detected through their chemical signatures in a galaxy at a redshift of about 6. The signatures were consistent with theoretical models of stars exceeding 1,000 solar masses. But even this finding, remarkable as it is, does not fully resolve the problem of MOMZ14. It explains the nitrogen enrichment as a possible product of an exotic stellar population. It does not explain why that exotic stellar population, and the galaxy in which it lives, existed at all at 280 million years after the Big Bang, at a luminosity 100 times greater than expected. The chemical enrichment problem, the luminosity problem, the ionization problem, 3 separate anomalies, each severe in isolation, each pointing in the same direction. Something about the early universe produced structure and complexity and chemical maturity far faster than our models predict it should have been able to. And the deeper we look with JWST, the more of these impossible things we find there are, as of mid-2025, not one but a growing population of galaxies at redshifts above 12 that share these properties to varying degrees. Luminosities wildly above predictions, chemical enrichments that require rapid stellar cycling, ionized environments that precede the general epoch of reionization by hundreds of millions of years. MOMZ14 is the most extreme, the record holder, the clearest example, the one whose properties have been most carefully measured and most thoroughly confirmed. But it is not alone. The universe, it is beginning to appear, learned to make things far more quickly than we taught it to, which raises the question that I find most haunting and most difficult to sit with comfortably. What are we missing? Not which parameter to adjust, not which simulation to refine, but what fundamental physical process or what fundamental ingredient in the cosmic recipe are we failing to include? 3 possibilities are on the table, 3 possibilities, each of which, if true, would transform our understanding of the universe's first billion years in ways that cannot be undone, and none of them can yet be ruled out. Science progresses almost always through the identification of a discrepancy and the systematic elimination of explanations. When JWST began returning data that challenged our models of early galaxy formation, the scientific community did not immediately declare a crisis. It did what it always does. It looked for the simplest, least disruptive explanations first. It asked whether the discrepancy was real before asking whether the discrepancy was profound. That process of elimination, of ruling out the mundane before confronting the extraordinary, is worth following carefully because it is how we arrived at the genuinely difficult question that MOMZ14 and its kin now force upon us. The first candidate explanation for the overabundance of bright early JWST galaxies was instrumental. Perhaps JWST was simply performing better than expected, collecting more light per hour of observation than the pre-launch performance predictions had modelled. This is, in fact, true. JWST's mirrors were kept cleaner during construction and assembly than specifications required, and its optical performance has consistently exceeded its pre-launch estimates. A telescope that gathers 10% or 15% more light than expected will detect more faint objects in any survey. This is a real contribution to the observed overabundance, but it is a small contribution. Instrumental overperformance can account for perhaps a factor of 2 in the observed galaxy counts, perhaps slightly more in specific brightness ranges. It cannot account for a factor of 100. It cannot account for MOMZ14. The second candidate explanation was simulation fidelity. The theoretical predictions for early galaxy abundance are generated by cosmological simulations, computer models that simulate the formation and evolution of structure in the universe, from the primordial density fluctuations of the CMB to the present day. These simulations have grown steadily more sophisticated over the decades, but they remain fundamentally limited by computational resources. A simulation of the full observable universe cannot simultaneously resolve the small-scale physics of individual molecular cloud collapse and stellar feedback within individual galaxies. The range of scales involved is too vast. Instead, these small-scale processes are captured by what modelers call subgrid physics, simplified parameterizations of processes that cannot be directly simulated. Several research groups pointed out in the early post-launch period that the standard simulations typically used to generate predictions for galaxy surveys undersampled the most extreme peaks of the primordial density distribution, the rare, exceptionally dense regions that would be the first and fastest to form structure. When simulations specifically targeted these rare overdense peaks, they found more luminous early galaxies. This is a genuine improvement in the models and accounts for a meaningful fraction of the observed excess, perhaps a factor of a few, bringing the overall discrepancy down from 2 orders of magnitude to something smaller, though not yet fully explained. The third candidate explanation was the bursty star formation mechanism described in the previous chapter. The idea that early galaxies formed stars in intense episodes rather than at a constant rate, temporarily inflating their luminosities above what their time-average star formation rates would imply. This is now fairly well established as a real physical phenomenon. There is direct observational evidence from JWST's own spectroscopic data on multiple early galaxies of episodic star formation, galaxies caught in the act of a burst and others caught in the quiet period between bursts. The mathematics of bursty star formation, combined with the observational bias towards selecting galaxies at their brightest, can account for another significant fraction of the discrepancy. The fourth candidate explanation was AGN contamination, that many of the seemingly superluminous early galaxies are actually ordinary galaxies whose total light output is being boosted by the accretion luminosity of a central supermassive black hole, an active galactic nucleus that outshines the stellar population by a large factor. This is also confirmed for a specific population of early JWST objects, the so-called little red dots, compact red-coloured galaxies found in large numbers in JWST deep fields. Many of these turn out, on detailed analysis, to be powered primarily or substantially by AGN activity, not by star formation, and their stellar masses are consequently much lower than their raw luminosities initially implied. So, 4 real physical effects, all confirmed by data, all contributing meaningfully to explaining the early JWST galaxy overabundance. The community converged by early 2024 on a consensus position that the broad galaxy abundance problem, why are there so many bright early galaxies, was probably explainable without fundamental modifications to the lambda CDM cosmological framework, provided all 4 effects were properly included in the models. That was the consensus. And then JWST GSZ14-0 arrived, and then, a year later, MOMZ14. Here is the reason these 2 galaxies, and particularly MOMZ14, resist the 4-factor explanation. They sit at the extreme end of the redshift distribution, redshifts of 14.88 and 44 respectively, in a regime where the combination of all 4 effects simultaneously, at their maximum plausible values, still falls significantly short of predicting objects this luminous. At redshift 10, the combined effect of the 4 factors brings theory and observation into reasonable agreement. At redshift 12, the agreement is strained. At redshift 14, the team itself, in the published paper for MOMZ14, explicitly states that even the most optimistic implementations of all 4 explanatory mechanisms leave the observed luminosity of MOMZ14 unexplained by a factor that remains uncomfortably large. Furthermore, MOMZ14 specific properties rule out the most significant of the 4 explanations, AGN enhancement, directly. Its compact morphology, its steep ultraviolet slope, and its lack of the broad emission line features characteristic of AGN activity, all indicate that its luminosity comes from stellar processes, not from a central black hole. This is the galaxy saying, in the language of its own spectrum, that it has built the light we see from stars. From star formation happening at an extraordinary rate in the present moment of its observation, a rate that has increased by a factor of roughly 10 within the last 10 million years of its existence. Which brings us to the three doors. Cosmologists and astrophysicists working on the early JWST galaxy problem have by now identified three broad classes of explanation for what MOMZ14 represents. Each class is physically coherent, each has adherents in the research community, and each, if proven correct, would have consequences for our understanding of the universe that extend far beyond the specific question of early galaxy formation. The first door leads into the physics of star formation itself. It posits that the early universe, the first few 100 million years, was a fundamentally different environment for star formation than the universe we know today, in ways that our current models fail to capture. The gas in those primordial dark matter halos was denser, more turbulent, and more compressed by the cosmic microwave background radiation, which at that epoch was still warm enough to fill the universe with a significant flux of photons that set a minimum temperature for the gas. Stars formed in these conditions were probably more massive than stars today. They burned hotter, they died faster, they produced ionizing radiation more efficiently per unit of stellar mass. If population 3 stars, or even a still more extreme population of supermassive stars in the mass range above 1, Zu-zero solar masses, were common in these earliest galaxies, then the relationship between a galaxy's total stellar mass and its luminosity would be very different from what we assume when we apply local universe conversion factors to JWST observations. A galaxy of 100 million solar masses, but composed entirely of stars 10 or 100 times more massive than typical stars today, would be far more luminous than a galaxy of the same total stellar mass composed of stars like the Sun. It would produce far more ionizing radiation per solar mass of stars, consistent with MOMZ14's apparent ability to ionize its surrounding environment. And when those massive stars died, after a few million years, not a few billion, they would produce supernovae and other explosive events that dispersed their heavy element yields efficiently, potentially explaining the rapid chemical enrichment observed in both MOMZ14 and JADE's GSZ14-0. This first door does not require any modification to the lambda CDM cosmological model. It requires only that we have underestimated how extreme the stellar populations of the very earliest galaxies were. It is, in that sense, the most conservative of the three doors, the one that saves the framework while revising its contents. The second door leads into the physics of dark matter. The standard lambda CDM model treats dark matter as cold, meaning it moved at non-relativistic velocities in the early universe, and essentially featureless, interacting with ordinary matter only through gravity. These two assumptions, combined with an initial power spectrum of density fluctuations set by cosmic inflation, produce a precise prediction for the distribution of dark matter halos at every epoch of cosmic history, how many halos of each mass existed at each moment in time, and how those halos grew. Several theoretical papers published since the JWST findings began accumulating have proposed that this dark matter halo mass function, the distribution of halo masses, may be wrong in the early universe for reasons related to either the properties of dark matter itself or the initial conditions of the primordial density field. If dark matter has any of a variety of non-minimal properties, if it is self-interacting, or if it converts from one type to another in the early universe, or if there is an additional component of what theorists call early dark energy that modifies the expansion rate of the universe in its first 100 million years, then the production of dark matter halos in the early universe could be more efficient than the standard model predicts, producing more massive halos earlier, and therefore providing the gravitational scaffolding for more massive galaxies to form sooner. The Hubble tension, the persistent, statistically significant discrepancy between measurements of the universe's current expansion rate obtained from the CMB and those obtained from relatively nearby distance indicators like Cepheid variable stars and Type ER supernovae is already motivating serious consideration of early dark energy models. These models propose a brief period of enhanced dark energy density in the early universe, before the epoch of recombination that would modify the sound horizon scale in the CMB and reconcile the tension in expansion rate measurements. Early dark energy models also, as a side effect, modify the growth of structure in the early universe in ways that could produce more or more massive dark matter halos at high redshifts. This second door is more radical. It does not abandon lambda CDM, but it modifies one of its most fundamental ingredients. And the modifications required to explain the most extreme early JWST galaxies, particularly MOM-Z14, may need to be substantial. The third door is the most radical of all, and the one that most physicists approach with the greatest caution because it involves questioning not just the details of the cosmological model, but one of its foundational assumptions: the age of the universe itself. There is a small but persistent community of researchers who have proposed, since the early JWST findings began accumulating, that the universe may be older than the 13.8 billion years that the standard lambda CDM model fitted to CMB observations implies. If the universe is older, if there was a longer period of time between the Big Bang and the epoch from which JWST is now observing these distant galaxies, then the impossibility of what we are seeing becomes somewhat less impossible. Galaxies that currently appear to have had only 280 million years to form would, in an older universe, have had 350 or 400 million years or more. That is not an enormous extra margin, but in galaxy formation physics, a few extra tens of millions of years can be the difference between possible and impossible. The proposals for a genuinely older universe are mathematically sophisticated and involve modifications to the standard description of the universe's energy content. Specifically, proposals for forms of dark energy that evolve differently in the early universe than the simple cosmological constant of the standard model implies. Some of these models reproduce the CMB acoustic peak structure and the large-scale distribution of galaxies reasonably well, while allowing the age of the universe to stretch by a few billion years. But they are, at present, constrained by a variety of observations that the standard model fits better, and none of them has achieved the kind of broad community acceptance that would warrant calling them a serious alternative to lambda CDM rather than a speculative proposal. 3 doors, 3 classes of explanation. And here is the genuinely unsettling truth about where the science stands today. We cannot currently determine which door leads to the correct answer. All 3 remain physically viable. The data from JWST is discriminating powerfully between the models. Each new galaxy confirmed at high redshift, each new spectroscopic measurement, each new chemical abundance determination adds new constraints to the space of possible explanations. But the question is not yet resolved. What we do know, what MOM-Z14 makes impossible to deny, is that the universe at 280 million years of age was already doing something that our best models said it should not be able to do for another 100 million years at minimum. The galaxy is there, the measurements are real, the redshift is confirmed by multiple independent emission lines. The chemical abundances are measured, the luminosity is documented. Something happened in the first 280 million years of this universe that we have not yet understood. And there is a person, a team of people actually, who have been living with this question for years, who pursued it across continents and institutions and telescope proposals, who built the survey specifically designed to find out whether these impossible things were mirages or miracles. Their story is the story of modern cosmology at its most human. Rohan Naidu is 32 years old or thereabouts, as of the confirmation of MOM-Z14. He is based at MIT's Kavli Institute for Astrophysics and Space Research, an institution whose very name evokes the kind of long-term, ambitious thinking that characterizes serious cosmological inquiry. He was born in India and grew up in a family where science was a serious conversation at the dinner table, not a subject reserved for school hours. He has described, in interviews, a childhood fascination with the scale of things, with the way that looking up at the night sky from a city creates a kind of vertigo, a sense that the ordinary categories of big and small no longer apply. By the time Naidu began his PhD, the astronomical community was already buzzing with the anticipated scientific returns of JWST. The telescope had been in development for so long, conceived in the late 1990s, formally approved in 2004, delayed repeatedly by technical challenges, cost overruns, and in 2020 by a global pandemic, that several generations of astronomers had built their entire research programs around the questions it was expected to answer. The deep field universe, the epoch of reionization, the first galaxies, these had been the promised territory of JWST for over a decade before it launched. What nobody fully anticipated, what even the most optimistic pre-launch modelers had not quite been willing to predict, was the scale of the surprises that would begin arriving within months of first light. When JWST began returning early universe data in late 2022, Naidu was one of the researchers at the front of the community's response. He was not alone. The JWST collaboration, whose name stands for JWST Advanced Deep Extragalactic Survey, involved hundreds of scientists across multiple institutions on multiple continents, and it was the JWST team that would eventually confirm JWST GSZ14-0 as the most distant known galaxy in 2024. But Naidu's particular contribution was to ask a question that, in retrospect, seems obvious but required considerable intellectual courage to articulate clearly at the time. The question was this: are these things real? Not in the trivial sense. Nobody seriously suggested that JWST was detecting ghost signals or systematic errors at the level that could explain the entire overabundance. But in the deeper sense, are the photometric redshift estimates, the distance estimates derived from the shape of a galaxy's light across multiple imaging filters without direct spectroscopic confirmation, reliable at the extreme end of the distribution. A galaxy flagged as a candidate at redshift 14 based on its photometric dropout is not confirmed as a galaxy at redshift 14 until a spectrum is taken and the spectroscopic emission lines are identified. Some early-stage candidates, when followed up spectroscopically, turned out to be at much lower redshifts. Closer galaxies whose unusual colours mimic the appearance of extreme redshift dropouts. The Mirage or Miracle survey was Naidu's response to this concern. If you want to know whether the apparent population of extremely high redshift luminous galaxies is real, if you want to resolve the fundamental ambiguity between Mirage and Miracle, you must take spectra. You must follow up the most extreme photometric candidates with the gold standard of confirmation. Spectroscopic redshift measurement from JWST's NIRSpec instrument, which can break a galaxy's light into its individual wavelength components and identify the telltale emission lines of ionized atoms. The MOM survey was designed to do exactly that for the brightest, most extreme galaxy candidates in the Cosmos field, the Cosmic Evolution Survey field, the largest deep survey of the universe ever constructed. The Cosmos field is a patch of sky covering approximately 2 square degrees, roughly 9 times the apparent area of the full moon as seen from Earth, that has been imaged by virtually every major telescope available to modern astronomy, accumulating data at wavelengths from X-rays to radio waves over more than 2 decades of observations. Within this field, JWST imaging had identified numerous candidate galaxies at redshifts potentially above 12, 13, and even 14. The MOM survey would test the brightest of them. The observing program required telescope time, precious JWST time, allocated through a competitive process that weighs proposals against each other and against the total available hours in the telescope's observing schedule. Winning a large allocation of JWST time for spectroscopic follow-up of extreme redshift candidates is not a trivial achievement. It requires convincing a review committee composed of other astronomers that the science case is compelling, the technical approach is sound, and the likelihood of significant discovery is high enough to justify the cost in terms of observations not conducted on competing targets. Naidu and his co-investigators made that case, and they were awarded the time. The observing runs began. Data arrived from JWST's near-spec instrument, spectroscopic measurements of extreme redshift candidates in the cosmos field, and one by one the confirmation rate told a story. Some candidates turned out to be mirages, lower redshift interlopers whose photometric properties had mimicked the appearance of objects further away. This was expected. Photometric redshifts, especially at the extreme end of the distribution, carry non-trivial uncertainties. The question was the rate. If the vast majority of high redshift candidates were mirages, the early JWST galaxy overabundance problem would dissolve as a systematic error in the photometric selection. If the majority were real, confirmed by spectroscopy to lie where the photometric data suggested, then the overabundance was genuine. The majority were real. And then, in one of those moments that happen rarely in a scientific career, but that define it permanently when they do, a particular galaxy appeared in the data. The photometric pre-selection had flagged it as a candidate at redshift approximately 14, a luminous source that appeared only in the long wavelength infrared filters, invisible at every shorter wavelength, exactly the signature expected of a galaxy beyond the Lyman break at that distance. When the NIRSpec spectrum came in, processed through the data reduction pipeline, something extraordinary emerged: emission lines. Not one, not two, but multiple. Triply ionized nitrogen, doubly ionized carbon, helium and oxygen, all identifiable, all at wavelengths consistent with a redshift of 14.44. Not approximately 14.44, precisely 14.44 plus or minus 0.2, an uncertainty of less than 0.2% in the redshift measurement, corresponding to a measurement of distance accurate to within the equivalent of 5 centimeters over every kilometer of the total journey. The light had been travelling for 13.53 billion years. The measurement was precise to 0.02 redshift units. The team's published paper, in the Open Journal of Astrophysics, uses the phrase "a cosmic miracle," not as hyperbole, but as a deliberate scientific statement derived from the design of the survey. The survey was called Mirage or Miracle. The methodology was, test whether extreme redshift candidates are real. MOMSI-14 is not a mirage. Therefore, by the survey's own internal logic, it is a miracle. The terminology is deadpan and precise, and when you understand the context, genuinely funny in a way that only scientists who have spent years on a specific problem can manage. But behind the deadpan terminology is something that I think deserves a moment of extended reflection because it captures something essential about what this discovery means for the people who pursue it. Pascal Oesch, Naidu's co-principal investigator on the MOM survey, is based at the University of Geneva. He has been hunting for the universe's most distant galaxies since his own PhD, using first the Hubble Space Telescope and later JWST to push the record further and further back in cosmic time. He was part of the team that discovered GNZ11, a galaxy at a redshift of approximately 10.96. At the time of its confirmation, the most distant spectroscopically confirmed galaxy known, using Hubble data in 2016. GNZ11, which existed 400 million years after the Big Bang, was a source of considerable scientific excitement when Oesch and his colleagues announced it. At the time, it seemed impossibly distant. Now, less than a decade later, GNZ11 does not even appear in the top 10 most distant galaxies known. The record it held, the boundary it marked, has been superseded not once but many times over by JWST. The horizon has moved. The telescope that replaced Hubble as humanity's eye on the early universe has not merely extended the previous instrument's reach by a modest factor. It has opened an entirely new era of observational cosmology, one in which the questions that seemed intractable a decade ago are being answered, and those answers are revealing new questions that are deeper and stranger than anything we had framed before. For Oesch, there is something almost philosophical in this progression. He has said in public discussions that what JWST has revealed about the early universe is not simply that galaxies formed earlier than expected. It is that the early universe was a fundamentally different place than astronomers expected. That phrase carries weight, coming from someone who has spent the better part of his career trying to characterize that different place. Not just different in scale or in detail, but different in kind, different in the processes operating, the efficiencies achieved, the timescales governing. Yi Li, a graduate student at Pennsylvania State University and a member of the MOM team, has spoken publicly about what it is like to be a young researcher in this specific moment of astronomy's history. Every few months, the record falls. Every few months, a new galaxy is confirmed at a redshift that was unimaginable to the previous generation of instruments. The timeline is accelerating, not just in the sense that JWST's survey programs are proceeding and accumulating data, but in the sense that the universe is being revealed, in real time, as more complex, more structured, and more chemically rich in its earliest epochs than anyone fully prepared for. For Li and her cohort, the generation of astronomers who began their careers in the JWST era, the fundamental questions of their field are being reformulated almost in real time. There is a particular kind of vertigo in that experience. When you are trained in a discipline, you absorb not just the facts and techniques, but the open questions, the problems that the field is working on, the answers that are known and the ones that are not. But what JWST is doing is not merely moving the needle on known open questions. It is revealing that some questions the field thought were essentially settled, like the general shape of the galaxy luminosity function at high redshifts, like the timeline of reionization, like the chemical state of the intergalactic medium in the first few 100 million years, are less settled than they appeared. The known unknowns are being transformed into unknowns about the known. Jacob Shen, a postdoctoral researcher at MIT and another member of the MOM team, has articulated the broader implication with a precision that I think deserves to be quoted because it captures the mood of a field that is simultaneously triumphant and unsettled. He has said, "There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. A growing chasm, not a resolved discrepancy, not a corrected model, a widening gap between what we predicted and what we find that is getting larger, not smaller. As JWST accumulates more data and more spectroscopic confirmations. And it is worth sitting with that for a moment, because in the popular presentation of science, discoveries tend to be framed as resolutions. The answer to the question is X. The mystery has been solved. The universe has yielded its secret. But MOMZ14 is not that kind of discovery. It is the opposite kind. A discovery that makes the mystery deeper, that transforms a known discrepancy between theory and observation into a documented gap of a specific measurable magnitude. Before JWST, the models predicted roughly how many bright early galaxies there should be, and observation was largely consistent with prediction. After JWST, the models predict one number of extremely bright galaxies at redshift 14, and observation finds roughly 100 times that number. The gap is not a rumour or an inference, it is a measurement. And Naidu's survey, the Mirage or Miracle survey, was specifically designed to make the gap undeniable, to remove every possible alternative explanation, to either confirm that these galaxies are mirages, artifacts of photometric errors that dissolve under the scrutiny of spectroscopy, or confirm that they are miracles, real objects at real redshifts that our standard models cannot produce. They are miracles. And MOMZ14 is the brightest one. What does it feel like to be the person who confirmed that? Naidu has said, in the ESA press release accompanying the discovery, that what JWST is revealing looks nothing like what we predicted, which is both challenging and exciting. There is a precision to that phrasing that I respect deeply, both challenging and exciting. Not just exciting. The discovery is not merely a triumph of observation or a record set for the sake of setting records. It is challenging, it creates work, it obligates the field to go back to its models, its assumptions, its foundational equations, and determine what has been missed. The human story embedded in MOMZ14's confirmation is not a story of triumph against adversity, as so many science narratives choose to frame themselves. It is a story of methodical precision deployed against genuine uncertainty. Naidu and his colleagues did not know, when they designed the MOM survey, that it would find the most distant galaxy ever confirmed. They knew that extreme redshift galaxy candidates existed in the cosmos field, and they designed a program to test their reality. The miracle was not something they were looking for specifically. It was something they were prepared to find or not find. By building the right tool and pointing it in the right direction, there is something profound in that model of inquiry. You do not chase miracles. You design the conditions in which miracles, if they exist, will be forced to reveal themselves. And then you measure what you find with every precision available to you, and you report it honestly, regardless of whether the result confirms what you expected or upends it entirely. MOMZ14 upended it entirely, and the team published the paper, with its extraordinary title, with its unambiguous language, with its complete spectroscopic confirmation, within weeks of the data being processed. Because that is what you do when the universe reveals itself. You describe what you saw as precisely as you can, and you invite the rest of the field to grapple with what it means. The rest of the field has been grappling ever since. But the implications of MOMZ14 do not stop at the boundary of galaxy formation physics, or even at the boundary of cosmological modelling. They extend outward into questions that bear on not just how the universe formed its first structures, but what the universe's ultimate nature and trajectory may be. The stakes are, to use the most precisely accurate word I can find for what follows, civilizational, not metaphorically civilizational, not in the sense of a discovery that reshapes our cultural relationship to the cosmos, but in the specific sense that the questions MOMZ14 forces open, the questions about dark matter, dark energy, the age of the universe, and the completeness of the standard model, are questions whose answers determine whether our most fundamental theoretical framework for understanding reality is correct or not. And a framework that is not correct is a framework that cannot be trusted to extrapolate. A framework that cannot be trusted to extrapolate is a framework that cannot reliably answer questions about the future, not just of galaxies, but of the universe itself. The lambda cold dark matter model, lambda CDM, is the most successful scientific framework for describing the large-scale structure and evolution of the universe that humanity has ever constructed. This is not a statement made carelessly. The model is called the Standard Model of Cosmology, for the same reason that the quantum chromodynamic description of particle physics is called the Standard Model, not because it is certain or complete, but because it is the most precisely tested, most broadly predictive, most rigorously constrained theoretical structure available, and because for decades it has passed every observational test we have thrown at it, with a consistency that borders on the embarrassing. Lambda CDM describes a universe whose total energy content divides into three components: ordinary matter, the protons, neutrons and electrons that make up everything we can see and touch, constitutes approximately 5% of the total; dark matter, a form of matter that interacts gravitationally but not electromagnetically, invisible to every instrument that measures light, constitutes approximately 27%, and the remaining 68% is dark energy, represented in the model by the Greek letter lambda, which Einstein called the cosmological constant and introduced into his equations of general relativity as a kind of repulsive energy density of empty space, a term that drives the accelerating expansion of the universe discovered in 1998 by Saul Perlmutter, Brian Schmidt and Adam Rias, a discovery that earned them the Nobel Prize in Physics in 2011. These numbers, 5% ordinary matter, 27% dark matter, 68% dark energy, are not guesses or theoretical preferences. They are the output of fitting the lambda CDM model to an enormous array of independent observational data, the temperature fluctuations of the CMB as measured by the Planck satellite, the large-scale distribution of galaxies as mapped by surveys like the Sloan Digital Sky Survey, the abundances of light elements produced by Big Bang nucleosynthesis, the distances to Type Ia supernovae, the gravitational lensing of background galaxies by foreground clusters. All of these datasets, spanning different cosmic epochs and different physical phenomena, are simultaneously consistent with a single set of 6 cosmological parameters. The agreement is extraordinary. It is one of the great scientific achievements of the late 20th and early 21st centuries. And yet the Lambda CDM model contains, at its heart, several ingredients whose physical nature remains completely unknown. Dark matter has never been directly detected as a particle. The most compelling theoretical candidate, the weakly interacting massive particle, or WIMP, has been searched for directly in underground detectors at particle colliders and through indirect astrophysical signals for over 3 decades. It has not been found. The constraints from these non-detections have eliminated most of the parameter space that the simplest WIMP models occupy, and yet dark matter must exist. The gravitational evidence for it is overwhelming, and so something is providing that gravity. Something is there. We have simply not identified what it is. Dark energy is, if anything, even more mysterious. The cosmological constant is consistent with the data, but it has a specific numerical value, 1.1 times 10 to the power of negative 52 meters to the negative 2 in SI units, whose origin from fundamental physics is not understood. Every serious attempt to calculate the expected value of the vacuum energy density from quantum field theory, the theoretical framework that describes the quantum properties of empty space, produces a value roughly 120 orders of magnitude larger than the observed cosmological constant. This discrepancy between the quantum field theory prediction and the observed value is, by many measures, the largest discrepancy between a theoretical prediction and an observation in the history of physics. Solving it, explaining why the cosmological constant has the value it has, rather than a value 10 to the power of 120 times larger, remains one of the deepest unsolved problems in all of theoretical physics. I will admit that this fact genuinely unsettles me every time I return to it. We have built a model of the entire universe. That model works. It predicts the structure of everything we can observe, and at the centre of that model sits a number, the cosmological constant, whose value we can measure precisely but cannot explain at all. It is like having a perfect map of an unknown country, and the scale bar on the map is written in a language no one can read. This was the situation before JWST launched. The standard model was extraordinarily successful at the scales where it had been tested. The CMB, the large-scale galaxy distribution, the solar neighbourhood. Its successes were genuine and substantial. Its failures were confined to specific regimes. The small-scale structure of dark matter halos, the so-called missing satellites problem, the Hubble tension that seemed like edge cases, boundary conditions, regimes where the details of astrophysics rather than fundamental cosmology might provide the explanation. MOMZ14 changes the character of that situation in a specific way. The discovery of a galaxy at redshift 1444, 100 times brighter than the models predict, is not merely a failure of a galaxy formation simulation at the small-scale end of the mass function. It is a failure at the interface between cosmological initial conditions, the properties of dark matter halos at the highest redshifts, determined by the power spectrum of primordial density fluctuations, the expansion history of the universe, and the properties of dark matter, and the processes of galaxy formation that turn those conditions into observed luminosities. If MOMZ14 is at redshift 14.44, and it is, the spectroscopic confirmation is unambiguous, then the dark matter halo in which it formed must have been accumulating mass since the very earliest epochs of cosmic structure formation. The mass of the halo required to host a galaxy with 100 million solar masses of stars is, by standard estimates, on the order of several billion solar masses, or roughly 10 to 30 times the galaxy's stellar mass. A dark matter halo of several billion solar masses at redshift 14.44 is a statistical extreme event, something that should exist in the observable universe, but only in the very rarest regions of the primordial density field. The question of whether there are enough such rare regions whether the primordial power spectrum contains sufficient power at the relevant scales to produce halos of this mass this early is a quantitative question with a quantitative answer that depends on the values of the lambda CDM cosmological parameters, and the answer, when computed carefully, is barely, at the very edge, possibly just within the statistics, if the star formation efficiency in this particular halo is at the theoretical maximum, possibly just outside the statistics, requiring either modified initial conditions or a longer formation time than the standard model provides. That possibly just outside is where the implications for the standard model begin to sharpen. The Hubble tension has been with us since approximately 2019, when the discrepancy between the local measurement of the Hubble constant, the current expansion rate of the universe measured using Cepheid variable stars and Type Ia supernovae in the relatively nearby universe, and the value inferred from the CMB using the lambda CDM model first achieved statistical significance above 5 standard deviations, the conventional threshold for a discovery, or, in this context, a confirmed anomaly. The two measurements give values of approximately 73 km per second per megaparsec, the local measurement, and approximately 4 km per second per megaparsec, the CMB inference, a difference of roughly 8%, but carried at a statistical confidence that makes dismissal as a random fluctuation essentially impossible. The Hubble tension means that the universe, measured directly today, appears to be expanding faster than the lambda CDM model, calibrated on the CMB, predicts it should be. The tension has been scrutinized exhaustively for potential systematic errors in either measurement. None sufficient to explain the discrepancy has been found. The most widely discussed theoretical resolution involves modifications to the early universe, specifically a period of enhanced dark energy density before recombination, called early dark energy, that would alter the sound horizon scale in the CMB and reconcile the expansion rate measurements. Early dark energy models are relevant to MOMZ14 in a specific and important way. If the universe contained a period of enhanced dark energy density in its first few 100,000 years, a period of effectively faster expansion, then the growth rate of density perturbations during and after that period would be modified. Specifically, faster early expansion tends to suppress the growth of structure. Overdense regions grow more slowly when the universe is expanding faster, because the expansion works against gravitational collapse. This suppression is the wrong direction. It would make the overabundance of early massive galaxies worse, not better, unless the early dark energy also modifies the initial power spectrum in a compensating way. Some researchers have proposed instead that what is needed is the opposite modification. A period of slightly slower expansion in the very early universe, prior to about 100 million years after the Big Bang, that would allow structure to grow faster and produce more massive halos at high redshift. This is sometimes discussed under the umbrella of modified gravity, theories in which the effective strength of gravity on cosmological scales differs from what general relativity predicts, or through proposals for interacting dark matter, in which dark matter particles lose energy to their interactions with each other, or with dark energy, modifying their clustering behavior on small scales. None of these proposals is the consensus answer. All of them represent genuine scientific work, with published papers, theoretical calculations, and observational predictions that can in principle be tested. Some of them, particularly those modifying the primordial power spectrum, would leave detectable signatures in the CMB that the Planck satellite's data can constrain. Others make predictions about the distribution of galaxy clusters at lower redshifts that surveys like the Dark Energy Spectroscopic Instrument, DESI, can probe. What MOMZ14 has done is raise the stakes on these questions. Before its confirmation, the overabundance of early JWST galaxies was a significant anomaly, but one that could potentially be explained within the standard model through the four-factor mechanism described earlier. After MOMZ14 spectroscopic confirmation, the anomaly at the extreme end, at redshifts above 14, is documented as a factor of 100 discrepancy that the four-factor explanation cannot close. The question of whether this requires new physics, not just improved astrophysics, but genuine modifications to the lambda CDM framework, has moved from the speculative to the serious dark energy, one of the least understood components of the universe's total energy budget, has been showing its own signs of restlessness in recent years. In 2024 and 2025, results from the Dark Energy Spectroscopic Instrument, a spectrograph mounted at the Kitt Peak National Observatory that has been mapping the three-dimensional distribution of galaxies across cosmic history with unprecedented precision, began suggesting that dark energy may not be a simple cosmological constant. The DESI data, interpreted through the standard cosmological framework, favours dark energy models in which the density or equation of state of dark energy varies over time. What physicists call dynamical dark energy, a cosmological constant does not evolve. It simply is at the same density everywhere in space and at every moment in time. A dynamical dark energy evolves, and its evolution leaves a specific imprint on the expansion history of the universe that a precise survey like DESI can detect. If dark energy is dynamical, if it is not simply a property of empty space but a field or a collection of fields that evolves over cosmic time, then everything our model predicts about the universe's future becomes less certain. The expansion of the universe, currently accelerating under the influence of the cosmological constant's repulsive effect, could accelerate faster or decelerate, or even reverse, depending on how dark energy evolves. The universe's ultimate fate, eternal expansion, or a future collapse, or a slow heat death, or a big rip, as accelerating expansion tears apart galaxies, then star systems, then atoms, depends on what dark energy actually is. And MOMZ14 is relevant to this because, if dark energy evolved differently in the early universe than the cosmological constant model predicts, and DESI data suggests it may have, then the expansion history of the universe at very early times may have been different from the lambda CDM prediction. Different expansion history at early times means different growth of structure. Different growth of structure means a different distribution of dark matter halos at high redshift, and a different distribution of dark matter halos at high redshift means different predictions for what JWST should see. Predictions that may or may not agree with what it actually sees. We are, in other words, at a moment when multiple independent observational programs, JWST's early galaxy surveys, DESI's dark energy measurements, the ongoing Hubble tension from local distance measurements, are simultaneously pointing toward the possibility that something about the standard model is incomplete at a foundational level. These three separate threads of evidence are not yet woven together into a single coherent alternative framework, but they are pointing in directions that are increasingly difficult to dismiss individually, and that, taken together, create a picture of a standard model under genuine observational pressure from multiple directions simultaneously. This is not a cosmological crisis. That phrase, which has appeared in headlines with troubling regularity since 2022, overclaims what the evidence supports. The lambda CDM model remains by far the best fitting, most precisely tested description of the universe we have. It is not collapsing. What is happening is something more subtle and, in many ways, more scientifically productive. The model is being pushed into new observational territory, and in that territory it is showing signs of strain. The size and character of that strain is being documented with increasing precision by instruments of unprecedented capability, and the documentation is forcing the field to take seriously ideas about the nature of dark matter, the behaviour of dark energy, the physical conditions of the very early universe that were previously speculative or marginal. MOMZ14 did not break the standard model, but it is one of the most precisely documented, most thoroughly characterized pieces of evidence that the standard model, in its current form, is telling us less than the complete truth about what the universe's first 100 million years was actually doing. That is the civilizational implication. Not the end of a theory, but the beginning of something that replaces it, or extends it. with something more complete, and identifying what that more complete thing might be requires confronting, with unflinching honesty, everything we currently do not understand, not as a list of open questions, but as a structured inventory of the most promising directions and the most dangerous assumptions, and the specific measurements that the next generation of instruments will need to make. Let me be precise about the claim, because precision is what separates a scientific argument from a narrative preference. MOM-Z14 is the most distant confirmed galaxy in the observable universe as of May 2025. It has a spectroscopic redshift of 14.44, confirmed by multiple independent emission lines. Its light was emitted 280 million years after the Big Bang. Its current proper distance from Earth, the distance accounting for the expansion of the universe that has occurred in the 13.53 billion years since its light was emitted, is approximately 33.8 billion light-years. It has a stellar mass of approximately 100 million solar masses, comparable to the Small Magellanic Cloud. Its diameter from the extent of its light profile is approximately 240 to 500 light-years. It is undergoing a rapid episode of star formation, with a star formation rate that appears to have increased by a factor of roughly 10 within the past 10 million years of its existence. It shows emission lines of triply ionized nitrogen in quantities exceeding anything observed in more mature, much larger galaxies. It is clearing ionized bubbles in the surrounding intergalactic medium. It is approximately 100 times brighter than pre-JWST galaxy formation models predicted anything at this distance and epoch should be. These are the facts. They are not contested. What is contested, what remains genuinely, productively, scientifically uncertain, is the interpretation, and the space of legitimate interpretation is wider than any single headline can capture. So let us walk through it carefully. The most significant uncertainty in interpreting what MOM-Z14 means is the question of whether its properties require modifications to the lambda-CDM cosmological framework, or whether they require only modifications to our models of how galaxies form within that framework. This distinction is crucial because the second possibility, revised astrophysics within an unchanged cosmological model, is by far the less radical, and because there is genuine, well-motivated evidence that our astrophysical models of early galaxy formation were incomplete before JWST, the four-factor explanation described earlier, improved JWST optics, better simulations, bursty star formation, and AGN enhancement, is real. It is not an ad hoc response to the data. Each of the four factors has independent physical motivation, and in most cases, independent observational confirmation. The fact that these four factors, even applied simultaneously and generously, fall short of explaining MOM-Z14's specific luminosity at redshift 14.44 does not mean they are wrong. It means they are insufficient at the extreme end of the distribution, at the very highest redshifts and the very highest luminosities, without additional contributions from physics we have not yet fully characterized. One specific area of active investigation is the stellar initial mass function, the distribution of masses of stars that form in a given star-forming event. In the local universe, the initial mass function is well characterized. It follows a roughly power law distribution, with many more low-mass stars forming per unit of total stellar mass than high-mass ones. This distribution determines, in part, how luminous a galaxy of a given stellar mass will be, because massive stars are far more luminous per unit of mass than low-mass stars. If the initial mass function in the early universe was systematically skewed toward more massive stars, as many theoretical arguments and some observational hints suggest, then the conversion from observed luminosity to inferred stellar mass would be significantly wrong for high redshift galaxies. A galaxy that appears, based on its luminosity, to have 100 million solar masses of stars might actually contain fewer stars of higher individual mass, and the total mass needed to explain the luminosity could be substantially lower than the standard conversion implies. A more top-heavy initial mass function in the early universe is not merely an ad hoc proposal. It is physically motivated. In the very early universe, the cosmic microwave background radiation had a higher temperature than today. The CMB temperature scales as 1 plus redshift, meaning at redshift 14. 44, it was approximately 15 times hotter than its current 2.73 Kelvin, or roughly 41 Kelvin. This elevated CMB temperature set a minimum temperature for the gas in star-forming regions. Gas cannot cool below the CMB temperature through ordinary radiative processes, raising the effective Jeans mass, the minimum mass that a gas cloud must exceed for gravity to overcome thermal pressure. Higher Jeans mass means larger minimum star size. The theoretical prediction, confirmed by multiple independent calculations, is that population 3 stars and the earliest population 2 stars formed preferentially in the mass range above 10 solar masses, with many forming at hundreds or thousands of solar masses. If MOM-Z14's stellar population contains a significant fraction of stars in these high mass ranges, then both its luminosity and its nitrogen enrichment become more tractable within the standard cosmological framework. More massive stars are more luminous per unit of mass, explaining the factor of 100 luminosity excess, without requiring an implausibly large total stellar mass. And supermassive stars, objects in the range of 1000 to 100 solar masses, if they existed in MOM-Z14's host environment, produce nitrogen through processes unavailable to ordinary stellar populations, potentially explaining the triply ionized nitrogen signature that is one of the galaxy's most puzzling spectroscopic features. This is the most conservative path through the anomaly. It preserves lambda CDM, it revises only the stellar physics inputs to galaxy formation models, and it is testable. Future JWST observations at higher spectroscopic resolution and future ALMA observations of the dust and gas content of MOM-Z14 and galaxies like it will constrain the stellar population models with increasing precision. The question of whether MOM-Z14's light comes from a standard stellar population or from an extraordinarily massive and exotic one is, in principle, answerable by further observation. But there is a second layer to the problem that cannot be resolved purely by revising the stellar initial mass function, and it concerns the dark matter halo in which MOM-Z14 lives. To form any galaxy, regardless of how efficient its star formation is, regardless of how massive its stellar population, you need a dark matter halo. The galaxy's stars form from gas that falls into the gravitational potential of the halo, and the halo's mass determines both how much gas can be retained and how quickly it can accumulate. For MOM-Z14 to exist at redshift 14, 44 with any stellar mass at all, a dark matter halo must have grown by that epoch to a mass roughly 10 to 30 times the galaxy's stellar mass. Given a stellar mass of about 100 million solar masses, the host halo mass is likely to be in the range of 1 to a few billion solar masses. A dark matter halo of 1 billion solar masses at redshift 14.44 is not impossible within the standard lambda CDM model. The power spectrum of primordial density fluctuations, normalized to the CMB observations, contains enough power at the relevant spatial scales to produce such halos in the observable universe. The question is one of abundance. How many such halos should exist in the volume of the universe that JWST surveys have explored by redshift 14.44, and does the one or more confirmed galaxies at this extreme redshift represent a number consistent with the statistical prediction? The answer from the MOMIM team's own analysis and from independent assessments by several research groups is barely consistent, at the absolute edge of what the standard model predicts, requiring star formation efficiencies at or approaching their theoretical maximum. Not clearly inconsistent, but not comfortably consistent either. The galaxy sits right at the boundary between explainable and anomalous within the standard framework. This boundary position is actually scientifically informative. It tells us that we are at the limit of what the current model can handle without modification. It is precisely the kind of signal that historically, in the annals of physics, has preceded either the recognition that a model needs modification or the recognition that a model is fundamentally incomplete. The photoelectric effect sat at the boundary of classical physics for years before Einstein's 1905 paper, explained it by postulating the quantum of light. The precession of Mercury's perihelion sat at the boundary of Newtonian gravity for decades before Einstein's general relativity explained it exactly. Scientific anomalies at the edge of a model's predictive power are not curiosities. They are the leading edge of what comes next. MOMZ14 is not the photoelectric effect of cosmology. It is too new, too singular, too recent in its confirmation for such a comparison to be warranted. But it is, along with the Hubble tension and the DESI dark energy results, part of a pattern of anomalies that collectively challenge the standard model at its boundaries. And the specific location of those challenges, the early universe, cosmic expansion history, the properties of dark matter and dark energy, are the same regimes where the standard model's physical content is least understood and most assumed rather than derived. What are the specific observational predictions that would distinguish between the three explanations: revised stellar physics, modified dark matter, or modified cosmology, that the field is now actively testing? The first discriminant is the number of additional extreme redshift galaxies that JWST finds in the coming years. The MOM survey is ongoing. The Cosmos Webb survey, a wide-field JWST imaging program covering several square degrees of sky, is accumulating data. If MOMZ14 is an extreme statistical outlier within the standard model, it should be nearly alone at its redshift. If additional galaxies are confirmed at similar redshifts with similar luminosities in the coming observing cycles, the statistical argument against the standard model's dark matter halo abundance function becomes significantly stronger. The second discriminant is the detailed chemical composition of these extreme redshift galaxies, measured through high-resolution spectroscopy with JWST's NIRSpec and future instruments, and through millimeter-wave observations with ALMA and its planned successors. The specific ratios of nitrogen, oxygen, carbon, and other elements in these galaxies encode the history of the stellar populations that produce them. A stellar population dominated by very massive or supermassive stars produces element ratios that differ in specific, calculable ways from a population with a standard initial mass function. If future spectroscopic surveys confirm that MOMZ14 and its contemporaries consistently show the chemical signatures of top-heavy or supermassive stellar populations, the case for exotic stellar physics, as the primary explanation, strengthens considerably. The third discriminant is the large-scale environment of these extreme redshift galaxies. If MOMZ14 sits in an unusually dense region of the primordial universe, the kind of overdense region that would produce a more massive dark matter halo than average at any given epoch, then its properties become more consistent with the standard model's halo abundance predictions. JWST can probe the environment around a high redshift galaxy by searching for companion objects, galaxies or bright star-forming regions that might be embedded in the same overdense dark matter structure. The Cosmos field has been imaged deeply enough that companions at similar redshifts, if they exist in MOMZ14's vicinity, should be detectable. Future observations targeting this question will provide direct information about whether MOMZ14 is part of an unusual cosmic overdensity, which would partially alleviate the statistical tension. The fourth discriminant comes from outside JWST entirely. The Square Kilometre Array, SKA, currently under construction in South Africa and Australia, will eventually map the distribution of neutral hydrogen across cosmic history through the 21 centimetre emission line of atomic hydrogen. This measurement will directly probe the epoch of reionization, mapping when and where the neutral hydrogen fog of the early universe was ionized by the first stars and galaxies. If the SKA detects ionized bubbles at redshifts corresponding to the epochs of MOMZ14 and JADE's GSZ140, it will confirm that these galaxies were already driving reionization far earlier than the standard model predicts. If the 21 centimetre map shows the intergalactic medium at those epochs to be uniformly neutral, except in the immediate vicinity of known bright sources, it will tell a more complex story about how localized the early ionization was. The fifth and perhaps most consequential discriminant is the CMB itself, specifically future CMB observations at higher angular resolution and sensitivity than the Planck satellite achieved. The CMB contains, encoded in its temperature and polarization fluctuations, the complete initial conditions for cosmic structure formation, the full primordial power spectrum from which all galaxies, all clusters, all cosmic filaments ultimately grew. If the primordial power spectrum is modified at small scales, if there is more power at the scales corresponding to the dark matter halos of galaxies like MOM-Z14 than the standard inflationary model predicts, that modification should leave a specific signature in the CMB that next-generation experiments like the Simons Observatory or CMBS-4 should be able to detect. There is one more consideration that I want to introduce here, because I think it is underappreciated in the public discussion of JWST's early universe findings, and it is important for understanding what MOM-Z14 does and does not imply. The lambda CDM model, in its current form, makes predictions based on 6 fundamental cosmological parameters: the Hubble constant, the densities of ordinary matter, dark matter and dark energy, the amplitude of primordial density fluctuations, and the spectral index of those fluctuations. These parameters are constrained by fitting the model simultaneously to multiple datasets. When a new observation appears that is inconsistent with the model's prediction at a given confidence level, the first response is to check whether the observational systematic uncertainties are understood. The second is to check whether the model is being evaluated with the correct parameter values, and the third, only after the first 2 steps are exhausted, is to conclude that the model itself needs modification. For MOM-Z14, the first step, checking systematic uncertainties, has been completed thoroughly. The spectroscopic redshift is confirmed beyond reasonable doubt by multiple emission lines. The luminosity measurement is straightforward from the detected flux and the confirmed distance. The systematic uncertainties in the stellar mass estimate are real. The conversion from light to stellar mass depends on assumptions about the stellar initial mass function and the dust extinction, but they are not large enough to change the galaxy's qualitative status as a factor of 100 outlier in the luminosity function. The second step, checking whether the model evaluation is using appropriate parameter values, is more interesting. The tension between JWST's early galaxy findings and the standard model's predictions depends on which values of the Hubble constant and other cosmological parameters are used in the model. In a universe with a higher Hubble constant than the CMB-derived 67.4 km per second per megaparsec, closer to the locally measured 73, the universe would be slightly younger at any given redshift. At redshift 14.44, the age difference between a universe with H0 equal to 67.4 versus H0 equal to 73 is roughly 20 million years. 20 million years earlier means 20 million fewer years for MOM-Z14 to have formed. This is the wrong direction. It makes the problem harder, not easier. Conversely, in a universe with a lower Hubble constant than the CMB value, one that expands slightly more slowly, the universe is older at any given redshift, providing more time for structure to form. Some researchers have noted that the early JWST galaxy overabundance could be partially alleviated by cosmological parameters that differ from the Planck, best fit in the direction of a slightly slower early expansion rate. Whether this is the correct direction of new physics is, as of now, unknown. The third step, concluding that the model needs modification, has not yet been reached by the broad community consensus, but it is within sight, and the specific measurements needed to confirm or rule out the need for modification, from the continued MOM survey, from DESI, from SKA, from CMBS-4, are either underway or planned. The timeline for resolution is not decades. It may be as short as 5 to 10 years. 5 to 10 years to determine whether the lambda CDM model, the framework that has guided cosmological thinking for 3 decades, is complete, or merely the best approximation we have been able to construct with the data available to date. That is a remarkable fact to sit with. We are not waiting for instruments that don't exist or technology that hasn't been invented. We are waiting for the analysis of data that is already being collected. The answer, or a much closer approach to it, is already somewhere in the universe, encoded in the photons already travelling toward our detectors, in the spectra already being processed on computers, in the surveys already underway in the telescopes we have built. We are right now in the period between asking the question and knowing the answer, and what makes that period genuinely electrifying and genuinely uncomfortable is that both possible answers are transformative. If MOMZ14 and its contemporaries are explained by exotic stellar physics within an otherwise intact lambda CDM framework, the result will be a profound revision of our understanding of the first stars and galaxies, a new chapter in the story of how ordinary matter organized itself in the universe's youth, a chapter that includes supermassive stars, top-heavy initial mass functions, extraordinarily efficient star formation, and a reionization history very different from what we previously assumed. And if MOMZ14 and its contemporaries require modifications to the cosmological framework itself, if the Hubble tension, the DESI dark energy signal, and the extreme high redshift galaxy overabundance are all manifestations of the same missing ingredient in the standard model, then we are at the beginning of a revision to cosmology comparable in scope to the introduction of the cosmological constant in 1998, a new ingredient in the cosmic recipe, a new term in the equations that describe the universe's expansion and the growth of its structures, a new physics. Both outcomes are extraordinary. Both would represent genuine advances in our understanding of the universe we inhabit. And neither can be determined from the data we currently have, which is exactly where science ought to be when it is working correctly. There is a question that runs beneath everything we have discussed, and it has not been asked directly yet, though it has been implied in every chapter. It is not a question about dark matter or stellar mass functions or spectroscopic redshifts. It is more fundamental than any of those. It is the question of whether MOMZ14 and the galaxy that preceded it as the record holder, and the galaxy that will eventually surpass it, is telling us something not just about the early universe, but about the universe's ultimate structure, about whether what we see, even with JWST, is everything there is to see, or whether our observable universe is itself a limited window into something far larger and far stranger. The observable universe, the sphere of space within which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years, not because the universe is that size, but because the expansion of space means that even light emitted at the Big Bang from regions that were then close to us has only now reached us from regions that have since moved to 46 billion light-years away. MOMZ14 sits at a proper distance of 33.8 billion light-years, closer to the observable horizon than to us, but still within it. There may be galaxies at distances beyond 33.8 billion light-years that JWST will eventually confirm, pushing the record further back toward the cosmic horizon. In fact, given the rate at which JWST has been breaking its own records, there almost certainly are. But there is a boundary that JWST cannot cross, regardless of how long it observes and how deeply it stares. That boundary is the epoch of recombination, the moment 380,000 years after the Big Bang, when the universe became transparent to light. Before recombination, the universe was opaque. No photon emitted in those first 380 zeros and years can reach us today, every one of them scattered off the plasma billions of times before finding its way into the CMB. The CMB is the ultimate backwall of the electromagnetic universe. There is no galaxy, no structured object made of ordinary matter, that JWST or any optical or infrared telescope will ever see from before that moment. The cosmos before recombination is inaccessible to light-based astronomy. It is, however, accessible to other messengers. Gravitational waves, ripples in the fabric of space-time itself, can propagate through the plasma of the early universe in ways that photons cannot. If the Big Bang produced gravitational waves, as inflationary models universally predict, those gravitational waves are still propagating through the universe today, carrying information about the very first instance of cosmic history. Detecting them requires an instrument sensitive to gravitational waves at extremely low frequencies, frequencies far below what LIGO and Virgo and their successors can reach. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the mid-2030s by ESA, is designed to detect gravitational waves in the millihertz frequency range produced by mergers of supermassive black holes and potentially by exotic early universe processes. While LISA's primary targets are astrophysical, its sensitivity may extend to primordial gravitational wave backgrounds. The relict gravitational wave signal from the inflationary epoch that would provide direct information about the physical conditions of the universe in its first fractions of a second. The Pulsar Timing Array program, arrays of millisecond pulsars distributed across the Milky Way, used as gravitational wave detectors by measuring tiny fluctuations in the timing of the pulsar's regular pulses, has already detected what appears to be a background of gravitational waves in the nanohertz frequency range, reported in 2023 by multiple independent collaborations. The origin of this background is debated. Supermassive black hole mergers are the leading explanation, but primordial gravitational wave backgrounds or exotic early universe processes remain candidates. This convergence of gravitational wave astronomy and the JWST era of deep field galaxy surveys is not coincidental. Both are probing the universe's early history through different physical channels, and the combination of electromagnetic observations of the earliest galaxies with gravitational wave observations of the earliest space-time perturbations offers, in principle, a multi-messenger picture of cosmic history that no single instrument or waveband can provide alone. But the specific next steps for understanding MOM-Z14 and the galaxy formation problem it represents are more immediate. The MOM survey itself is ongoing. Having confirmed the most distant galaxy known, Naidu, Oesh, and their collaborators are continuing to process spectra of additional extreme redshift candidates in the cosmos field. The survey was explicitly designed to confirm multiple objects at the highest accessible redshifts, not just to claim a single record. Each new spectroscopic confirmation, or non-M, of a candidate above redshift 12 is a data point in the statistical picture of how the galaxy luminosity function behaves in the epoch of cosmic dawn. The Cosmos Webb Survey, a larger area JWST imaging program that covers approximately half a square degree of sky compared to the smaller areas of the JDES and MOM survey fields, is accumulating photometric data that will identify hundreds of new extreme redshift candidates for future spectroscopic follow-up. The combination of Cosmos Webb's breadth with the MOM survey's spectroscopic depth is expected to produce, over the next 2 to 3 years, a statistical sample of galaxies at redshifts between 10 and 15 that is large enough to constrain the shape of the luminosity function at these epochs with meaningful precision, not just its normalization, but its slope, its cutoff at the bright end, and its evolution from epoch to epoch. That statistical sample is what will definitively distinguish between the three explanatory doors. A luminosity function that steepens sharply at the highest luminosities, consistent with the Standard Model's prediction that the most massive halos are exponentially rare, would support the interpretation that 14 is a genuine statistical extreme within an otherwise intact lambda CDM framework. A luminosity function that remains flat or even flattens at the bright end. Too many very luminous objects compared to the model would indicate that the Standard Model's halo abundance prediction is wrong at high redshifts, requiring either modified cosmology or a fundamentally different formation channel for the most massive early objects. The implications also extend to one of JWST's original and most important scientific goals: mapping the timeline of cosmic reionization. The universe transitioned from fully neutral hydrogen immediately after recombination to a fully ionized intergalactic medium by approximately 550 million to 1 billion years after the Big Bang, the conventional range for the end of the epoch of reionization. This transition was driven by the ultraviolet photons from the first stars and galaxies, which ionized the surrounding hydrogen gas and gradually cleared the cosmic fog. MOMZ-14's apparent ability to ionize its local environment at 280 million years after the Big Bang, at least 270 million years before the general reionization of the intergalactic medium is thought to have been completed, suggests that the earliest stages of reionization were driven by objects even more extreme than those typically included in reionization models. If MOMZ-14's ionizing photon production rate per unit stellar mass is significantly higher than standard assumptions, as the presence of very massive or supermassive stars would imply, then the total ionizing photon budget of the early universe, summed over all galaxies like it, may have been substantially larger than reionization models based on a standard stellar initial mass function assume. The timeline of reionization, and the sources that drove it, may both need revision. This has a direct observational consequence. The 21 centimeter signal from neutral hydrogen in the early universe, which SKA will map in unprecedented detail starting in the late 2020s and early 2030s, should show the imprint of early reionization driven by sources like MOMZ-14. If sources at redshift 14 are already ionizing significant volumes of the intergalactic medium, the SKA's 21 centimeter maps should show patchy, partially ionized regions at these epochs, clustered around the positions of the brightest early galaxies. This prediction is specific and testable, and it connects directly to JWST's spectroscopic findings through a chain of physical reasoning that can be followed in both directions. There is also the question of what MOMZ-14 will eventually become. At 280 million years after the Big Bang, MOMZ-14 has a stellar mass of 100 million solar masses and is undergoing intense star formation. What is its eventual fate? This depends on questions we cannot yet answer from current data. The mass of its dark matter halo, the gas supply available for future star formation, and whether its current star formation burst will trigger feedback that quenches further activity or sustain itself through continued gas inflow. The Milky Way galaxy, by comparison, has a stellar mass of approximately 60 billion solar masses, 600 times larger than MOMZ-14's current mass, and has been forming stars continuously for approximately 13 billion years. If MOMZ-14's dark matter halo is sufficiently massive, and if its gas supply is sufficiently continuous, it could in principle grow into a massive galaxy over the subsequent 13 billion years of cosmic history. It might be the progenitor of something like an early type elliptical galaxy, the old, red, star formation-quenched galaxies that dominate the cores of massive galaxy clusters today, and that are themselves among the most puzzling objects in observational astronomy, because they appear to have formed the bulk of their stars very early, and then stopped, a history that the standard model of galaxy evolution struggles to explain. Alternatively, MOMZ-14 might be what it looks like, the early counterpart of a small galaxy, something that will grow over billions of years into an object not unlike the small Magellanic Cloud in our own galactic neighbourhood, or perhaps a member of a future galaxy cluster's population of low-mass satellite galaxies. What is certain is that MOMZ-14 in its current observed state represents a galaxy in the act of becoming. It is not a finished object. It is a process caught in mid-course, a furious, luminous, chemically enriching process that is assembling itself from the primordial material of the universe at a pace and with a chemistry that challenges everything we thought we understood about how that assembly was supposed to proceed. And there will be more. The MOM survey will find more. Cosmos will find more. Whatever comes after JWST, the Habitable Worlds Observatory planned for the 2040s, or the next generation large space infrared telescope that will eventually carry the torch forward, will find more. The record at redshift 1444 is not a wall, it is a threshold. The universe extends beyond it, into a regime of redshifts above 15, above 16, perhaps above 20, where the first galaxies of all, the very first concentrations of stars ever to ignite in a previously dark universe, are waiting to be detected by instruments we have not yet built or have only begun to plan. every step further back in time that astronomy has managed. From Hubble's confirmation of galaxies beyond the Milky Way, to the discovery of quasars at cosmological distances, to the first detection of galaxies at redshifts above 3, above 6, above 10, above 14, has revealed that the universe at those earlier epochs looks different from what was expected. Different and stranger and richer. The history of observational cosmology is a history of assumptions overturned by data, of expected simplicity replaced by unexpected complexity, of the universe proving itself more willing to produce extreme and beautiful objects earlier, and more efficiently than any model predicted. MOMZ14 is the latest entry in that history. It will not be the last. And what lies beyond it? What waits in the regime of redshifts above 15 that JWST is now beginning to probe and that future instruments will eventually illuminate, is something that science does not yet know how to fully characterize. We have, with MOMZ14, pressed our eye to the edge of the window that our current best telescope has opened onto the early universe. The view through that window is already shocking. What the next window will show is something we cannot yet imagine, except to say that if the pattern holds, if the universe continues to be more structured, more luminous, more chemically complex at every new horizon we reach than the last model predicted, then the horizon beyond MOMZ14 will be at least as surprising as MOMZ14 itself. That is not a prediction that requires courage to make. It is the lesson of every observational advance in the past century of astronomy. Look further, see more, and what you see will be stranger than what you expected. There is a passage in the history of physics, not a dramatic moment, not a discovery, just a moment of recognition, that I find myself returning to whenever a story like this one threatens to overwhelm the capacity of ordinary language. In 1905, the physicist Ernst Mach, who had spent decades insisting that the concept of an atom was metaphysical nonsense, a theoretical convenience with no physical reality, read Einstein's paper on Brownian motion, which demonstrated that the random jiggling of microscopic particles in suspension was a direct and measurable consequence of molecular bombardment. Mach is reported to have said approximately, "Now I believe in atoms." He had spent a career certain he was right. He was wrong. And he had the intellectual honesty to say so, simply, without qualification, when the evidence demanded it. There is something about that moment, of a person who has built their understanding of reality around a framework, confronting a measurement that the framework cannot accommodate, and choosing to update their understanding rather than defend the framework, that I find deeply moving. Not because Mach's certainty was admirable, it wasn't, but because his willingness to revise it was. We are in a moment that has something of the same character, though the story is less resolved, the players more numerous, and the stakes, at the civilizational level I have tried to describe, far higher than any single scientist's investment in any single framework. MOMZ14 is a galaxy. It is a faint smear of infrared light in a patch of sky in the constellation Sextans, so small in angular extent that it would take millions of them placed side by side to span the apparent diameter of the full moon. It is 8 billion light-years away, and yet we have measured its distance to within a fraction of a percentage point. We have identified the chemical species present in its interstellar medium, nitrogen, oxygen, carbon, helium, at a moment 280 million years into the universe's 13.8 billion year history. We have inferred the temperature of its gas, the rate at which it is forming stars, the mass of its stellar population. We have determined that its immediate neighbourhood is partially ionized, against the background of a universe that should not have managed this feat for hundreds of millions of years to come. We have done all of this with a telescope, golden mirrored, sunshield protected, operating at minus 233 degrees Celsius at 1.5 million kilometres from home. That itself represents the accumulated effort of thousands of engineers, scientists, project managers, and administrators working across 30 years and across an international consortium of nations, sustained through delays and cost overruns and political pressures and a global pandemic and the ordinary grinding attrition that any project of sufficient ambition and sufficient duration must endure. And what we have found, at the end of all that effort, is something that doesn't fit, something the model did not predict, something that sits at the edge of what the framework can accommodate and looks out over the edge into the unknown. I find this, and I mean this without any performance of wonder, as a plain statement about my actual response to this material, genuinely one of the most affecting scientific situations I have encountered. Not because the anomaly is resolved, it isn't. Not because the answer is at hand, it isn't. But because the anomaly is real, documented, measured, confirmed, and because it is asking questions that we have not yet learned to answer. The universe does not owe us comprehensibility. It does not distribute its wonders at a pace and convenient for our models or our timelines. It is not waiting for us to catch up. At 280 million years old, in a universe less than 2% of its current age, MOMZ-14 was already blazing with 100 times the light our models said it should have had any right to produce, already chemically rich, already clearing the fog, already becoming what it was going to be. We were not there to see it happen. We are only now, 13.53 billion years later, collecting the photons it sent us as it burned, reading the message that its light has carried across the expanding universe for a distance of 33.8 billion light-years. And finding in that message not an answer to the question of how the universe made its first structures, but a new and more precise statement of the question itself. There will be answers. Science always finds ways toward them, even when the paths are longer and stranger than anticipated. The MOM survey will continue. Cosmos Web will deepen its inventory. SKA will map the 21-centimetre sky. DESI will refine the dark energy measurements. CMB-S4 will push the cosmic microwave background observations to their next level of precision. And somewhere in the intersection of all those datasets, somewhere in the space between what we currently predict and what we currently observe, the shape of a more complete framework will begin to emerge. But MOMZ-14 will not be answered by any single future observation. It will be answered gradually by the accumulation of everything, by the patient and relentless process of science doing what science does, measuring, testing, refining, revising, and pressing further. That process is not finished. It is barely started. And perhaps that is the point. Not to arrive at the explanation of MOMZ-14 and then move on, as if the universe has yielded the last of its surprises, but to follow the question of how the universe learned to build things so fast, so early, with such chemical richness and such blazing light, all the way to its answer, knowing that the answer will open 3 more questions, each one deeper and stranger than the last. The universe at 280 million years old was already, impossibly, making things. We are still learning what that means, and I suspect we will be learning it for a very long time.